All right, this is AP BC Calculus, Unit 6, Section 13. This is a BC only section. We're learning about improper integrals. So if you are an AP AB kiddo, please skip to 614, which is the next video, to practice integration techniques. So today we're going to learn about improper integrals. Improper integrals come in two main varieties. Integrals with an infinite bound, right, thus unbounded, so something like uh, integrating from, let's say, 5 to infinity, right? Or integrals with a vertical asymptote in the middle, which is also unbounded. In both cases, we're going to address the problematic bound, the infinity or the asymptote, by using limits. In lieu of using that problematic number as the bound, we label it as a letter and then evaluate the limit as we approach the value. Depending on the circumstances, it might be a left, a right, or a double-sided limit. If the integral has an infinitely large value, positive or negative, we call it divergent. If an integral has, if the integral, not interval, so integral, come on brain, has a finite value, then the integral is convergent and converges to that finite value. All right, so let's go ahead and walk through what to do about this. Okay, so we're going to integrate from 0 to infinity of e to the negative x dx. So this is what makes this an improper integral. The way we're going to handle it is we're going to go ahead and call this b. So we're going to say that this is the limit as b approaches infinity of the integral from 0 to b of e to the negative x dx. Now technically this is u sub, where your u is negative x, but when we integrate e to the negative x, essentially we're just doing the opposite of the chain rule for differentiating. We're going to have to divide by a negative 1. So what's going to happen is this is going to be the limit as b approaches infinity of a negative e to the negative x, right? And again, if you need the extra step to physically show that it's u sub, you can do that, but I would suggest that you're going to have an easier time if you don't. So I'm actually going to rewrite this as a negative 1 over e to the x, because that's what that negative x means, right, from 0 to b. So when we go to plug in, this is going to be the limit as b approaches infinity of a negative 1 over e to the b minus, right, so that'll be minus a negative 1 over e to the 0. And I don't need the limit on the second part of the bound because the limit really only applies to the top boundary. Well, this is going to end up being the limit as b approaches infinity of negative 1 over e to the b plus a 1, right? Well, because this is going to be infinitely large, a finite number, negative 1 over something infinitely large is 0. So this is 0 plus 1, and this entire thing approaches a 1, okay? But again, you can't actually treat infinity as a bound. You have to do the limit as that b approaches infinity. So you're going to go ahead and give another one a try. So same idea, right? This is the issue. So what we're going to do is we're going to go ahead and integrate this. Now, hopefully you're looking at this and spotting that this is an arctan. So this is the limit as b approaches infinity of the integral from 0 to b of 1 over 1 plus x squared dx. So here my a squared is 1, so a is 1. My u squared is x squared, so not only is u x, but du is dx. So this is basically as straightforward of an arctan as you can get. So this is the limit as b approaches infinity of the arctan, or inverse tan, I don't care which one you write, of x evaluated from 0 to b, right? So what's going to happen is we're going to get that this is the limit as b approaches infinity of the arctan of b, which we'll deal with in a sec, minus the arctan of 0, right? So remember, arctan is saying what angle has this value, right? Like what angle has the value infinity, right? So if we think about what an arctangent looks like, right? An arctangent essentially looks like this. So the way an arctan looks, right? So this is a horizontal asymptote at pi over 2. This is a horizontal asymptote at negative pi over 2, right? This is what an arctan graph looks like. This is y equals the arctan of x, right? So essentially the limit as, so arctan of 0 is 0, right? Because this, so hopefully we know why arctan of 0 is 0, but it's saying It's saying tangent of some mystery angle gives you 0. Well, the tangent is 0 when sine over cosine is 0, which is at 0. So this is a 0. And if you look at this graph, right, you want to know as your values approach infinity, what is the arctan approaching? Well, it's approaching a pi over 2. So you're going to get pi over 2 minus 0, and so your answer is pi over 2. So not only do you need to write these improper integrals as limits, but then you also have to know the information to evaluate the limit. All right. Okay, so we're going to integrate 1 over x cubed with respect to x from 1 to infinity. So the same argument, I have to do this as the limit as b approaches infinity of the integral from 1 to b of 1 over x cubed dx. Now remember that this 1 over x cubed is actually an x to the negative third dx, right? So that's going to end up being the limit as b approaches infinity. I'm going to up the power by 1 and divide by the new power. So what's going to happen is this is going to be a negative x to the second over negative 2 from 1 to b, which I'm probably going to rewrite because it's a little ugly the way it's written, right? I'm probably going to rewrite that as a 1 over a negative 2x squared, right, from 1 to b. So when I plug in, I'm going to get this is the limit as b approaches infinity of negative 1 over 2b squared, which we'll deal with in a sec, minus this 1 over, and again, you can make the negative on the top or the bottom. I made it on the bottom here. Might as well make it on the top. A 2 times a 1 squared, right? So this thing ends up being a 0 because I have a negative 1 on top of something that's infinitely large. So I'm going to get 0 plus 1/2, which is 1/2. So far, all of these have converged to a numerical value, but they're not all going to converge to a numerical value. So let's deal with what happens when they don't. So go ahead and try and integrate this one. This is a simple natural log formula. The only trick is that you have to make it the limit as b approaches infinity because you can't have an infinity as your bound. Right, so this is going to integrate to natural log. We're going to get the limit as b approaches infinity of the natural log of the absolute value of x from 1 to b. So that's going to be the limit as b approaches infinity of the natural log of the absolute value of b minus a natural log of 1. Well, the natural log of 1 is definitely 0. That's great. But if you picture what a natural log graph looks like, this goes up forever. So as we approach infinity to the right, we're also approaching something infinitely large. So I get something infinite, which means that this is divergent. You can either say divergent or you could say diverges. Okay, all that means is it has an infinite value, not a finite value. So your answer isn't actually infinity. Now occasionally on an AP test, they'll give infinity as a choice instead of the word divergent or diverges, but realistically, most of the time you'll be given the word, not the infinity symbol. All right, so what you saw in E2 and P2 actually has a name. These are called P-series. So a P-series is essentially a 1 over x to a power. And in general, you can actually make a quick assumption about this. This will converge for p-values that are bigger than 1, and we saw that in E2, right? See how this was, p was a 3, right? And it converged. And it will diverge for p-values that are less than or equal to 1. And we saw that here, where p was 1, because that's an x to the first on the bottom, and sure enough, it diverged. So a couple quick notes. The p-series doesn't have to start at 1, and here's the logic. If a p-series converges, that means that it has a finite value, right? It has a finite sum. And if you were to start it at 2 instead, you removed some of the quantity, right? Because you were integrating, you're finding the area from 1 to infinity. Well, if 1 to infinity is a finite number, right? So if whatever you're integrating, let's say you start at 1 and you integrate to infinity, and this thing looks like this, right? If this is a finite number, then if instead of starting at 1, you start at 2 and you only want this piece, well, that also has to be a finite number. So if this converges starting at 1, it's also going to converge starting at 2. By the same argument, if this thing is infinitely large, it's not going to matter if you cut off a little bit of the edge. It's still infinitely large, because if you subtract a finite amount from something that has an infinite size, it won't change its infinite size. The second piece of information is it doesn't matter if there's a number on top that's not 1. Because let's say there was a 5 on top here, right? Let's say that I had a 5 up here. Well, I would just treat it as a 5 times the original thing that I showed you. So it doesn't matter that if there's a number up top, okay? So neither of those will impact the nature. Any finite number, even if that finite number is huge, it wouldn't change whether something converges or diverges. All right, so moving on. All right, so let's go ahead and integrate. Now we're going to do the other kind of issue that I discussed, which is that you also have problems around vertical asymptotes. So see how this thing has a vertical asymptote at x equals 2? Well, 2 falls in the window between 0 and 4. So basically what we're going to have to do is we're going to have to treat this as two separate pieces. We're going to have to say, oh, I'm going to find the area on the left side of the issue, and I'm going to find the area on the right. So what we're going to do is we're essentially going to split this into two integrals, right? We're going to split this into the integral from 0 to 2, because 2 is a vertical asymptote, and from 2 to 4. But I'm still going to have an issue that I can't actually use the 2's that are here because they are still improper. I can't use 2 because the function is not continuous at 2. So I'm going to recognize that I can't use these numbers. So I'm going to say that this is the limit as b approaches 2. So if you picture the window from 0 to 2, so here's 0, and here's 2, and here's 4. This window is going to be approaching 2 from the left because you're approaching this way, of 0 to b, right, of this value, right? And then this integral is going to be the limit as, and I'm going to use a for the bottom bound, as we approach 2 from the right, because we're to the right of 2, from a to 4. So as weird and tedious as this seems, the one thing I do want to point out is that it's pretty easy to find the antiderivative because you're going to find the same one twice, right? It's still 6 over an x minus 2 in both cases. So what's going to happen is I'm going to get that this is the limit as b approaches 2 from the left of a 6 natural log of the absolute value of x minus 2, evaluated from 0 to b, plus the limit as a approaches 2 from the right of the exact same integrand, from a to 4. So now when we plug in, I'm going to get that this is the limit as b approaches 2 from the left of a 6 natural log of b minus 2, right? Minus, and when I plug in 0, I'm just going to get 6 natural log of 2, right, which we'll deal with in a sec. Plus, when I go on this side, I'm going to get that this is the limit. I don't need the limit for the top bound, my bad. The top bound's just a 4. So when I plug in the 4, I'm going to get 6 natural log of 2, right? And then the bottom bound is going to end up being minus the limit as a approaches 2 from the positive of this 6 natural log of a minus 2. Cool. So these two sum to 0, which is just fine, right? So that's fine. They sum to 0. But for these, I'm going to have to consider what this limit looks like, right? Okay, so if you picture what a natural log of b minus 2 looks like, right? So that's, we know natural log usually has its intercept at 1, right? And a vertical asymptote at 0. So what's happening here essentially is this graph, the natural log of b minus 2, because of the minus 2, it's shifted to the right 2. So it's got its vertical asymptote here, but also it has this absolute value. So what's happening is it looks like this on this side and then behaves this way on this side, right? But it does still have this vertical asymptote, right? It does still have this vertical asymptote. And this graph would work for both of these because they're both doing the same thing. One of them is approaching from the left, so this is a negative infinity. These sum to 0. This one is approaching, negative infinity, approaching from the left. This one is approaching from the right because it's also a negative infinity, plus a negative infinity. So I end up getting something that is super infinitely large. They're both negative infinities. Oh, I'm sorry, I take that back. It's a plus negative, it's a minus a negative infinity. And you might say, okay, cool, well, that's great. Minus a negative infinity would be plus infinity, and then they'd cancel to 0, but that's not how it works, because once you have infinitely large things, this diverges. So the difference I want you to spot between this and some of the others are that when I had infinities here, I never had an infinitely large value. I'd plug in an infinity and it would end up on the bottom, not the top, right? The issue here is that as soon as you start having infinitely large values, you're looking at a divergent integral. So, whoops, sorry, I went too far down. So because I have infinite values, even though you might say, oh, look, it's a negative and a positive infinity, that's not how infinities work. As soon as you start getting infinite values, you're looking at something that diverges. All right, so go ahead and try this one. So we're going to do 1 over x, right? So same basic logic. There is a vertical asymptote here at x is 0, right? So essentially, you're going to have to split this into the integral from -2 to 0. But again, there's a vertical asymptote here, so we're going to have a problem, right? minus, sorry, plus, my bad, the integral from 0 to 1 of 1 over x dx. And again, this is a problem. So we're going to have to treat this as the limit as b approaches 0 from the left, negative 2 to b, 1 over x dx, plus the limit as a approaches 0 from the right, integral from a to 1 of 1 over x dx. Both of these integrate just to the straight up natural log of the absolute value of x. So this is going to be the limit as b approaches 0 from the left of natural log of the absolute value of x evaluated from negative 2 to b, plus the same limit except with an a and 0 from the right of this exact same thing from a to 1. So when we plug in, we're going to get that this is the limit as b approaches 0 from the left of natural log of absolute value of b minus the natural log of 2. Here I'm going to get plus the natural log of 1 minus the limit as a approaches 0 from the right of natural log of the absolute value of a. So again, the trick is if you look at what a natural log graph looks like, it looks like this, but because the absolute value, the other side is doing the exact same thing. So both of these are approaching negative infinities. The second I involve an infinity, it doesn't matter what anything else is. It doesn't matter that there's a plus and minus infinity. It doesn't matter the second that there's an infinity. It diverges or it's divergent. So you don't have to say that it's negative infinity or positive infinity. You just have to say divergent. All right, let's do example 4. So again, you'll notice that we're looking at a vertical asymptote here, right? There's a vertical asymptote at negative 3. So essentially, we have to split this into two sections. We have to split this in a section from negative 4 to negative 3 and from negative 3 to 0, right? So what's going to happen is that we're going to get that this is the limit as b approaches negative 3 from the left of the integral from negative 4 to b of this 2 over x plus 3 quantity cubed, right? Plus the limit as a approaches negative 3 from the right of a to 0 of this 2 over x plus 3 quantity cubed dx. So it's not a terrible thing to just spot that you, like off to the side if you want, if you're integrating 2 over an x plus 3 to the third dx, if you need u sub to do this, that's great. If you don't need u sub, that's also great. This is a 2 over a u cubed, which means that what we're integrating is a 2u to the negative third du. So we'd up the power by 1, divide by the new power, right? So we're going to end up getting that this is a negative 1 over u squared, right? If you were just doing this piece of information ahead of time, right? So it's not awful to be able to integrate that off to the side because the limits alone are kind of annoying and complicating the situation. So we're going to go ahead and make this negative 1 over x plus 3 quantity squared from negative 4 to b, right? Plus, this is going to be the limit as a approaches negative 3 from the right of that same thing, right? A negative 1 over x plus 3 quantity squared from a to 0. Okay, so now let's go ahead and plug in, right? So we're going to end up getting that this is a negative 1 over b plus 3 quantity squared limit as b approaches negative 3 from the left minus a negative 1 over what seems to be a 1, right, because it'd be a negative 1 squared, right, plus this is going to be, when I plug in a 0, negative 1 over a 9, right, minus the limit as a approaches negative 3 from the positive of a negative 1 over this a plus 3 quantity squared, right? So let's picture what negative 1 over x plus 3 quantity squared looks like as a graph. It has a vertical asymptote at negative 3, and both sides are going to do this, right? So because, and you can check by plugging in values, but because it's squared, that's what's going to happen. Both sides are going to go in the same direction, right? So what's going to happen is this is going to end up being, when we approach from both sides, it's going to end up being a negative infinity. So we're going to get negative infinity plus 1 minus a ninth, and then plus an infinity. But again, we've seen this before. The second that we get an answer that's infinitely large, it doesn't matter. The answer is that it's going to be divergent. Infinities don't cancel that way, right? That's not how it works. A plus infinity and a minus infinity don't cancel. Okay, so same concept, right? So same concept, and here we're going to see the vertical asymptotes at 1, right? So what's going to happen is we're going to have to do the limit as b approaches 1 from the left. We're going to integrate from 0 to 1 of this thing, plus the limit as a approaches 1 from the right, and we're going to integrate from 1 to 4 of this thing. Again, if you want to do the actual integration somewhere off to the side because it's easier, you could recognize that this is a 3 over u squared du, right? So that's a 3u to the negative second. So when you integrate, you're going to get a 3u to the negative 1 over negative 1, which means you're going to get a negative 3 over u, essentially. So we're going to get that this is the limit as b approaches 1 from the positive of a negative 3 over x minus 1 from, sorry, that wasn't a 1. That was a b, and that was an a. My bad, people. From 0 to b, plus the limit as a approaches 1 from the positive. Sorry, this one was from the negative. Man, I'm having an off problem. Anyway, of negative 3 over x minus 1 from a to 4, right? When we plug in, again, you're going to be looking at a graph that hopefully we have an idea what it looks like. All right, so 1 from the negative, we have this negative 3 over b minus 1 plus a negative 3 over negative 1, right? And then this will be a negative 3 over 1 minus the limit as a approaches 1 from the positive of a negative 3 over minus 1, right? So what's going to happen here is that, again, we're looking at a vertical asymptote. If you look at what negative 3 over x plus 1 looks like, it's got an asymptote at negative 1, and it's going to look like this. So this side's approaching a negative infinity. These two sum to 0. And then this side's approaching a positive infinity, so that's going to be minus a positive infinity. So it's going to be divergent. But again, the second you have infinities involved, you're looking at something that's divergent. All right, so when we go to plug in here, right, so just to show you the reason we have an issue here and the reason this is improper is because 2, right, would be a vertical asymptote for this graph, right? If you were to look at the graph of what's in the integrand, 2 would create a problem because you get 8 minus 8 in the denominator, which is, so we have to treat this as the limit as b approaches 2 from the left, because we're approaching from values between 0 and 2. Of the integral from 0 to b of this 3x squared over cube root of 8 minus x cubed dx. So I'm going to suggest that you do your u sub work off to the side without bounds, as I've suggested pretty much since the beginning. So I want to integrate this 3x squared over this cube root of 8 minus x cubed with respect to x, right? So my u is going to be the 8 minus x cubed. My du is conveniently going to be a negative 3x squared dx, which is basically this numerator but off by a negative. So I get du over the negative 3x squared is my dx. When I plug everything in, I'm going to end up with a negative 1 over a u to the 1/3 du. So we're going to rewrite that as a negative times a u to the negative 1/3 du. When I up the power by 1, I'm adding 3/3, so I'm going to get that this is a negative u to the 2/3 divided by 2/3, which we know is the same as multiplying by 3/2. So that's what I'm going to end up plugging in here. So this is the limit as b approaches 2 from the left of negative 3/2 8 minus x cubed to the 2/3, right, evaluated from 0 to b, right? So that's going to be the limit as b approaches 2 from the left of negative 3/2 8 minus b cubed to the 2/3 minus a negative 3/2 8 minus 0, so just 8 to the 2/3. Okay, so the trick here is that this is a polynomial, so it's continuous. So approaching from the left or approaching from the right doesn't really matter. It's the same as plugging in, so this is going to turn out to be a 0. And this is going to end up being a plus 3/2, and then we need to remember what 8 to the 2/3 is, right? 8 to the 2/3 is the same as cube root of 8 quantity squared. That's the easy way to do it. So that's a 2 squared, so this is a 4, right? So we're going to end up getting that this is a 12 over 2 or a 6, right? So that does have a conversion value, which I think is a nice breath of fresh air because we've done several problems in a row now where we didn't have a value that converged. So it was nice that we have a value that converges. So go ahead and try P5, same concept. You'll notice again that if you try to plug the 2 in here, you're going to get a problem. So you're going to have to do this as a limit, right? It's going to be the limit as b approaches 2 from the left of the integral from 1 to b of this thing. And again, I'm going to suggest that your best bet is to go off to the side and do your u sub work, right? So I'm going to separate it clearly and say, hey, here's my work. It's definitely not equal to that other stuff. If I integrate a 4x over this cube root of x squared minus 4. If I call my u the stuff on the inside in the denominator, which is the smart call, I get that du is 2x dx. So I'm going to get du over 2x is my dx. So I'm going to end up getting that there's a 2 that doesn't cancel from the top. So essentially this is a 2 over a u to the 1/3 du, right? Which means we're integrating a 2u to the negative 1/3 du. So I up the power by 1 and get a 2/3, and then I divide by 2/3, but that's the same as timesing by 3/2. So I'm going to get a 3, because 3/2 times 2 would just be 3, u to the 2/3. That's what I'm going to be plugging in here. So I'm going to get that this is the limit as b approaches 2 from the left of a 3 x squared minus 4 to the 2/3, sorry, we'll say it's a b, minus this 3 times, when we plug in a 1, we're going to get the cube root of -3, which is ugly, but is just genuinely where we're at. That's the best we get. So I get a cube root of -3. Well, when I plug this in, because this is a nice happy polynomial, I just get a 0. So I end up getting that this is the negative, it's a -3 cube root of -3. And that's really as good as it gets. You could yank the negative out of the cube root, because a cube root of -1 times a cube root of 3, right, would just be a -1 times a cube root of 3. So if you wanted, you could yank a negative out, and you could just make this a 3 cube root of 3, which would be the same answer. So this answer would be fine. You are allowed to take a cube root of a negative. You're not allowed to take a square root of a negative. So either of those are fine, and that's about as nice as it gets. So again, this converges, and it converges to that particular value. That's kind of the gist of how these work. And it can be a little bit difficult, but you get the idea of how these work.